8.3.1, double check your name and today's date are in your notes. Today's lesson will be information from 8.3.1 and 8.3.2. They're a continuation of each other. 8.3.1 starts with how can I write an equation? So make sure your eyes are on page 409. Make sure your notes are set up. Pencils are out. It says writing multiplication equations. The first two sections of this chapter involved data. In this section, you will focus on equations. In lesson 7.3.4, you began solving equations that contained addition or subtraction, such as x plus 18 equals 25. You solved these equations using several informal strategies. You also learned how to solve them by undoing with inverse operations. In this section, you will look at another group of equations. This group of equations contains multiplication or division. In this section, you will explore how to solve these equations, starting with writing and solving equations in the form of a times x equals b. Let's go back to our thinking from chapter 7 and remind ourselves even how to solve an equation in general. So let's put an example in our notes. It's the one that's mentioned in that paragraph I just read. X plus 18 equals 25. Our job in any equation is first to be able to identify that it's an equation. An equation has an equal sign. So off to the side, we're going to write the word equation, and then we're going to write equals equal sign. It's important to know. An equation contains expressions, one on each side. Here's an expression, something that can be solved. Here's an expression. Sometimes it's just a constant like this is. Other times there's a whole nother part on this side. And we've got to combine like terms and isolate our variables to solve for whatever the variable may be. In an equation, our job is to isolate, I want you to write this, the variable. To isolate something means to get it by itself. Let's highlight the word isolate. I'm going to draw an arrow. It means get it by itself. You want the variable on one side of the equal sign all by itself, so that it basically will say x equals and then something. It means it's been solved. You figured out what the variable is equal to. The variable will not always be x. Obviously, we know it will vary. It could be any letter technically. Sometimes our equations, they tell us what the variable is equal to. We plug them in and we solve them. Other times, they don't tell us what the variable is equal to, but we just got to get it by itself so we can figure out what the variable is equal to. This is one of those cases. They are not telling us what x is equal to. They are telling us that we need to find out what x is equal to by isolating x. We've got to get x by itself. In order to get a variable by itself, you'll use inverse operations. So get it by itself by using inverse operations. E looks crazy. It looks like an O to me. The inverse of addition is what? Subtraction. The inverse of multiplication is division. So inverses are opposites. Up here, in order to get x by itself, we are going to do the opposite of what's stuck with x. Right now it says x plus 18. So what's the opposite of adding 18? Subtracting 18. If we do it on one side, the rules say we have to do it on the other side. So if I do minus 18 here, I do minus 18 here. Positive 18 and negative 18 gives me how much?
0.
0. That's why we do the opposite, is to get it to go away. And the math rules say if we do it on one side, we must do it on the other. Or if we do it on the bottom, we must do it on the top. So it always has to be balanced. When this happens, we have a subtraction problem set up now. I cannot take 8 from 5, so I have to regroup, making this 15. 15 minus 8 is how much? 7. 1 minus 1? 0. This leaves me with 8x is equal to 7. So I solved by isolating my variable. You guys remember when we did this? We did it for a while back in chapter 7. We're going to take this same idea, same rules. We isolate the variable by getting it by itself by using inverse operations. When we use the inverse, this time we're going to focus on multiplication and division. So if I have a number stuck right with the variable indicating multiplication, in order to get rid of it, I'm going to divide by that number on both sides, or vice versa. And we're going to practice that today, okay? So we are going to, let's look at 8-84. In your book, it says, Margaret is trying to enlarge some diagrams to make several posters for a presentation. She decided on a multiplier of 5, so she's going to multiply by 5 to make the diagrams easier to read from far away. Margaret wonders how much she can enlarge each diagram so that it is the largest it can be while still fitting on the poster paper. The poster paper measures 36 inches by 48 inches. Margaret started answering her question by making the table at the right. So she wants to multiply by 5 every time, okay? So we're going to start the table. So for part A, we're going to sketch her table. We're going to continue to use it also. So the width of the original, so I'm just going to write width original. And then the width of when she enlarges it. So I'm write width enlarged. So if she starts with a 1 and she multiplies it by 5, how much is it enlarged to? 1 times 5 is how much? 5. Okay. These are both in inches, by the way. If she starts with 2, how big does it become when you multiply by 5? 10. What about if she starts with 3? 15, right? We're multiplying by 5 according to what the rules say each time. It says, help Margaret by writing an expression that represents the width of the enlarged diagram if her original diagram is R. So if her original is R, what is she doing to that R every time? Times 5, right? All you have to do is put a 5 right next to the variable to indicate 5 times R. You could write it like 5 times R, but this is more common to write. You just put the number right next to the variable. 5 times R. So whatever R is, if you multiply it by 5, that's what this is showing. So this is an expression. Now we're going to make an equation where we can figure out any time we're using R, if we multiply it by 5, we're going to get something. B says, write and solve an equation to determine the widest diagram that Margaret can use and have it still fit on the poster paper if she positions the paper so that it is 36 inches wide. So we need to be able to figure out, okay, if she says 5 times R, the biggest that she can get is 36 inches. Then how big can R be? 5 times what to get it as close to 36 as possible? Now, just in my head right now, 5 times a whole number is not going to get me to 36. Do we all see that? Yeah. If we know our multiples of 5, right, we know 5 times 1, 5 times 2, 5 times 3, and so on. We know that 5 times something gets me very close, but it doesn't end in a 5 here, nor does it end in a 0, so we know it's not going to be a whole number. But what is my closest whole number that I'm going to get to start with? I saw a lot of hands go in the air. Marco, what's my closest whole number?
40.
5 times 40? 5 times 8. That goes over, right? We can't go over So 5 times something that doesn't go over but is as close as we could get. Genevieve? 7. So 5 times 7 is equal to how much? 35. So we know it's going to be 7 and something, right? Because there's got to be a little piece that gets us to that additional 6. The easiest way to solve this is we need to isolate the variable. Right now it says 5 times r. What's the inverse of multiplication? Division. So if this is showing multiplying, we're going to divide. 5 divided by 5 is 1, correct? Yep. 1r and just r is the same thing. If I divide by 5 on one side, gotta do it on the other side. This says 36 divided by 5. So I need to set up that problem. 36 divided by 5. You already told me 5 times 7 is 35. So we started the problem. Gives me 1 left over. When I have my remainder, it becomes my numerator. And my original denominator becomes my denominator. And I'm done. 7 and 1/5. So r, if... That also be 7.5. Correct. 0.2. Yes, 0.20, which is 0.2. So 7 and 1/5 inches. Or as Tony said, we could do it in decimal, and we could do 7.2 inches. Either one is a correct answer. I would take it in fraction form or decimal form because they're equivalent. This is the one that I showed you, so that's what I'm going to circle. Okay. Yes, ma'am.
Before you did the problem, you can tell because you can tell it's going to be this because that's what you have.
Totally.
But then it's how many more you have if it's not a whole number. So like, the next one is 40.
Yes.
So I was like, oh, this is so
You're right. You can tell by knowing your multiplication facts, right?
Mm-hmm.
Absolutely. Very good eye. All right, I'm going to turn my page because I ran out of space. B is asking us basically the same question, but this time it wants to know the length. Okay, so using another equation, what is the longest diagram that Margaret can use and have to still fit the poster paper if she positions it so that 48 inches is wide, right? So first she had it turn this way. Now she's going to turn it this way. So what was the length is now going to become the width. Do we all follow? Okay. So same thing. She's still using a multiplier of 5. So that's the first part. But this time they're saying, look, the width is going to be 48. So very same strategy. If this is saying 5 times r, we undo it by doing the inverse. And the inverse of multiplication is division. Whatever's there, that's what you divide by. They cancel because 5 divided by 5 is 1. Whatever I do on one side, I've got to do on the other. This says 48 divided by 5. So I set that up. 48 divided by 5. Same strategy. Think about your multiplication. 5 times what gets me as close to 48 as possible without going over? Without going over. Dylan. 9. 5 times 9 is what? 45. Thank you. So 8 minus 5 is 3. That becomes my numerator. And I use my original denominator. The leftover is the numerator. The original denominator is the denominator. Okay. So 9 and 3/5 inches. So r is equal to. You'll just jump right in with this, okay, Kaden? Okay. Question, Maddie? Okay. Questions so far on isolating the variable with multiplication? It doesn't matter what number's here. If this was 3/5 times r, then we would divide by 3/5. And we would divide by 3/5. And we know how to divide by fractions, and we're going to practice dividing by fractions today. So it might not always be a whole number stuck with the variable. Keep that in mind. We start off kind of simple, and we get more complex. All right. Here's the more complex part where we're going to multiply and divide with fractions now. Okay. So 8-85. Raymond took Margaret's enlarged posters and reduced them. So he's shrinking them back down by using a multiplier of 1/6. Remember when we multiply by fractions, it actually makes things smaller. Do we remember that? Okay. So they would fit into a tiny pocket reference book. A says make a table that shows the width of Margaret's original diagram and the width it would be in Raymond's book. So here we're looking at 1/6. And we're trying to figure out, okay, if I have, and we're not going to make a table, we're going to just do the math. How about that? Let's do A. And her original was 5 times R. But he's taking that and he's multiplying that by 1/6. Raymond took Margaret's enlarged posters. So here's her expression. And he's reducing them by using a multiplier of 1/6. So he took the 5 times R and he's multiplying it by 1/6. Let's do this first before we do anything else. Okay, so let's simplify this. We haven't even set up an equation, but we have this expression that looks messy. So let's work on this. Right now, this literally says 1/6 times 5R. So that's a lot of multiplication, yes? So we're doing 1/6 times 5 is what we're doing. So let's ignore the R for a minute because this is basically saying 1/6 times 5 times R, right? Because 5 times R times 1/6. So there's 3 different multiplication pieces happening when I look at this. I want everybody to write with me. Anything I'm writing, you're writing with me. You have to solve 2 pieces of multiplication at a time. We can't do anything with R. So I'm going to ignore it for a minute. I can do 1/6 times 5. I'm going to do it right here. 1/6 times 5. What do I got to do to that 5? I have to put a 1 on the bottom. Multiplication with fractions is wonderful. You just multiply straight across. 1 times 5 is how much? 1 times 5? 5. 6 times 1? 6. So I'm going to rewrite it because I still have this R hanging out, right? 5, 6 times R. So 1/6 times 5R. So I showed it visually what my brain's thinking about. 1/6 times 5 times R is what this shows. I did the portion I can actually do. 1/6 times 5 right here. Now I have that times the R that's still stuck there. Everybody follow? Okay. So this is my new multiplier. Are we okay? Okay. So it says for B, write an expression that represents the width of the diagram in Raymond's book if Margaret's original diagram is R. This is it. This is the expression we're going to use to multiply by. We just need to write it there. Part C says Raymond's book is only 4 inches wide. Write an equation to determine the widest diagram that Margaret can use and still fit in Raymond's book. So we're going to use what we started with. And this time they're saying it's only 4 inches wide. That's as big as it can get. This says 5/6 times R. What's the opposite of multiplication? Then we've got to divide by 5/6. Whatever I do on one side, got to do on the other. These 2 cancel, they're done. So I'm left with R is equal to 4 divided by 5/6. That looks like this, my friends. 4 divided by 5/6. Fraction division. Lots of options. Skip, flip, and multiply. Common denominators. You do you. You figure out which one you like. A lot of you have already made that choice. Some of you say, depends on the numbers. I think that's the most efficient strategy, is look at the numbers you have and determine which one you think will be the fastest for that problem. For me, looking at this, I'm thinking, let's try skip, flip, and multiply. Okay, so you skip the first number, you flip the second number over, and you multiply in the middle. Problem is that 4 can't just hang out as a 4. What do I got to do to it? Yeah. Now I'm looking at a problem that's very similar to this type of problem. 4 times 6? 6 times 4? There we go. I know we sometimes prefer it to be in a certain order. 1 times 5? Okay. Can I leave this like that? No. This is why some people like common denominator division, because you got to end up dividing most of the time anyway. You divide the bottom into the top. Can 5 go into 2? No. Can 5 go into 24?
Yes.
How many times? 4. Which is 20. So So it leaves me with 4 left over. 4 goes up in the numerator, and the original 5 is the denominator. So 4 and 4/5. How are we doing so far? Okay. Oh, I need inches on there, don't I? Label my units. Okay. We're just practicing adding, subtracting, multiplying, and dividing with whole numbers, fractions, and decimals. This is practice. Okay. All right. Let's jump into 8.3.2. But before we do, I lied. I'm sorry. Let's do one little practice, and probably we'll do 2 little practices, and I'll pull sticks once I give you it. We'll do one at a time, okay? So the first one we're going to do, this isn't right before your review preview. Are you there with me?
Yeah.
I believe on mine it's page 800. Yours is probably not.
411.
Okay. See? Way off. All right. Let's look at A. This says 5/7 times D is equal to 15. What I want you doing by yourself, and for some of us, we're going to be a little stuck, and just pause if you feel like you can't go further. We will go over it as a whole group. Isolate your variable. This says 5/7 times D, so you'll divide by 5/7. Divide by 5/7. Then you need to show me 15 divided by 5/7. You could do common denominator division. You could do skip, flip, and multiply. If you're stuck, you just pause. Everyone should try. Go as far as you can. For some of us, that means you're going to isolate your variable. You're going to get D equals whatever you get, if you can go all the way. If you can't, if you're stuck, just pause where you can't go any further. I'm going to give. Alrighty. So, magic, huh? Alrighty. So I divided by 5/7 on both sides. These two cancel. That's why I divide by 5/7. That leaves me with 15 divided by 5/7, which is 15 divided by 5/7. I chose skip, flip, and multiply. I wrote 15, and then I flipped over the second fraction, so 5/7 became 7/5. Multiply. I multiplied straight across. 15 times 7, I needed to work it out. I did 15 times 7. That 105 is here. 1 times 5 is here. Again, if you don't have this in your notes, you need to be doing this with me. This says 105 divided by 5. 105 divided by 5. 5 could not go into 1. 5 went into 10 2 times, which is 10. Left me with nothing, so I dropped down the 5. 5 goes into 5 1 time, which is 5. I'm done. There's nothing left over, so it's 21. So D is equal to 21. Okay. In this case, there were no units, so there's no units necessary. Just D is equal to 21. All right, Genevieve, you just scored 50 points for Team 3. You may use your basketball and come try to take a shot next to Monica. Is B. Let's look at B. Okay. Right now, B says K divided by 12 is equal to 4. What is the inverse of division? Multiplication. So put a multiplication symbol, put a 12. These will cancel. Put a multiplication symbol, put a 12. Solve it. It's always funny to me and not surprising at all, actually. Students at first look at these that have the division already there and they're like, but then to solve it, because the opposite of division is
Multiplication.
It's always much easier to solve. Okay, 2 minutes, Jonathan. All right, let me unfreeze this. So this says K divided by 12. So the inverse of division is multiplication. So here's my multiplication symbol. I'm doing K times 12. Cancel, cancel. So whatever I do on one side, gotta do it on the other side. Thank you, Marco and Tony. They're like the only voices I'm hearing right now. 4 times 12 is what I'm trying to do to solve for K. So I set it up, 12 on top, 4 on the bottom, so that I distribute when I do my multiplication. 48. Some of you may know this in your head. That's wonderful too. So K is equal to 48. All right. Yeah. Alrighty. I'm just out of space, so I'm going to come to my next page. You guys can go right underneath where you are. You can just draw a line. But this lesson leads right into what we were just doing. Okay, so we're going to use this multiplication and division, adding and subtracting of equations to use some very common equations you will use in the real world. So name again if you're at the top of a page. If you're not, you're okay. 412?
Yeah.
Perfect. All right. So 8.3.2, what is the relationship? That just means how are they going to work together? Distance, rate, and time. Throughout this course, you've been developing skills for writing equations to describe relationships in tables and graphs and situations. Today, you will use your equation writing skills to represent the relationships between rate, time, and distance. So, 8-95. Anything I'm writing, you're writing with me. Let's stay focused. We have about 10 minutes. Axel's getting his pig ready for the pig races at the county fair. During the race, 4 juvenile pigs run along a straight track, trying to be the first pig to get a cream-filled chocolate cookie. His pig, Hammy, can run at a rate of 11 feet per second. A. At this speed, how far will Hammy run in 3 seconds? In 5 seconds? In 1 minute, which is 60 seconds, right?
Yeah.
All right, so 11 feet per second. So 11 feet in 1 second. This is our rate.
So basically, if you run like 2 seconds, all you gotta do is do like 2 times 11.
Correct? Yes. Per really just means that we're going to multiply, right? So when we set this up, we're comparing the relationship of feet per second, okay? So we need to figure out 3 seconds. So if this is 3 seconds, we've got to figure out, well, how many feet is that? Okay, so in order to go from 1 to 3, we multiplied by 3. And whatever we do on the bottom, you do it to the top. So it's 33 feet. Okay, what if it were 5 seconds? Okay, same thing. So 5 seconds, 55 feet. Okay, what if it were 60 seconds?
66.
Yeah, you're going to do times 60 times 60, right? Because 60 seconds is a minute. So 60 seconds. If you're sitting here just watching me and you're not writing, you need to have this in your notes. 60 times 11. If we don't know it, we do the math. Okay. 1 times 0? 0. 1 times 6? 6. Cross it off. Hold its place. 1 times 0? 1 times 6? Add it together. 0, 6, 6. 660 feet. Okay. Again, this needs to be in our notes. Now, B says, write an expression that represents how far Hammy will run in X seconds. Every single time, it was 11 times something, right? So if we're saying X for the amount of seconds, it's 11 times X. That's our expression. However many seconds you give me, I'll multiply it by 11. Because that's what we did here, and that's what we did here, and that's what we did here. That's what the expression is. Okay? C now gives us more information where we can take this expression and turn it into an equation, something we can solve. The racetrack at the fair is 150 feet long. Draw a diagram that shows how long it will take Hammy to finish the race. No. Let's do the math, okay? So 11 times a certain amount of seconds, and this is how far he has to go. You should have this written down. Some of you are looking around the room. How do I isolate this variable? What's my first step? Somebody has a quiet hand. Walk me through. What's my first step? Tony, what's my first step?
You divide 11 by both of them.
So I divide by 11?
Yeah.
Where first?
11.
Over here?
Yeah.
Okay, so I divide by 11. What happens here?
They get crossed out.
Yep, they cancel. What's my next step, Tony?
11 150 divided by 11.
Yeah, divide by 11 on this side, right? Whatever I do on this side, I've got to do on this side. Okay? So now it says 150 divided by 11, just like Tony says. I'm going to rewrite that so that I truly see 150 divided by 11. That means 150 divided by 11. Do you see how I'm showing the same math problem in 3 ways?
Yes.
150 divided by 11. 150 divided by 11. This is the only way that I can actually do an algorithm with, right? That tells me what to do. That tells me what to do. I can actually do it here. This is the algorithm. That means that's the equation. That's how I can set it up to be solved. Can 11 go into 1? No. 11 into 15?
Yes.
How many times?
1.
1 time. 11 times 1 is 11. 5 minus 1?
5. 4.
4. 1 minus 1? 0. Bring down the next 0. 11 into 40? 3 times, which is what? 33. Can't take 3 from 0. Regroup. Make that 10. 10 minus 3? 10 minus 3? 7. Okay, then boom. 13 and 7/11 times. Okay, so it asks, write an equation to represent the situation. We did. Okay, now about how long is what D is asking. Well, we found out exactly how long, right? It takes exactly 13 and 7/11 of a second. If someone says, well, about how long? You'd say between 13 and 14 seconds, right? Some of you would round down, some of you would round up. A reasonable answer is about what?
14 seconds.
Yeah, okay. Because what is half of 11? What's half of 10?
5.5.
5. So half of 11 is 5.5, right? 5.5. Is this more or less than 5.5? More. So it's got to go up, right? So reasonable answer is something like between 13 and 14 seconds or about 14 seconds. Either one in real life, that would be an answer someone would say. So D, about how long will it take Hammy to finish the race? Please write me a complete sentence. Yours may be different than mine. That's okay, as long as it's a reasonable answer. You've got data to support it. This is your argument. This is your analysis of your argument. This is your evidence. Analysis. Same process in language arts and math, just with numbers.
Is that going to be it?
Say it again.
Is that going to be it?
No. Question, Maddie?
Can I read it or no?
Sure, I'd love to hear it.
It will take Tammy about 15 seconds to finish the race.
Very nice. Very clear. Anybody else want to share? Marco?
It will take Tammy about 14 seconds for her to finish the race.
Perfect. Very clear. Anybody else? Thank you, Kaden.
It would take about 14 seconds for the kid to go from the beginning to the end.
Excellent. Very nice. Alrighty. Let's look at 8-96. No, I lied. Let's not look at 8-96. Let's jump to it. How about that? Let's look at 8-101. It's in review preview. We're going to skip to the hard stuff. You guys have got this. We just need to practice. Review preview. You with me? 8-101? Okay. A train travels at an average rate. Rate, we should be thinking ratio. Ratio, we should be thinking fraction. Okay. Of 40 miles per hour. This is what that looks like on paper. 40 miles per 1 hour. And travels for 110 miles. Okay. 40 miles per hour. So really, whatever I plug in for the hours, I'm going to multiply it by 40. You follow?
Mm-hmm.
Okay. Then it says it travels for 110 miles. Okay, so the total, right? for this example is 110 miles. 110 miles. I really should have put total above that. Sorry. Boop. There's my fraction line. What I don't know is how many hours that's going to take. But I could figure out 40 times something to get to this, right?
40 miles in an hour.
40 miles in 1 hour. Yep. So that's the speed limit, right? Is in this case, we see 60 or we see 40 or we see 25. Those numbers on the sign are telling us how many miles you're allowed to travel in an hour. It's your speed limit.
We're going to Texas, and there's a part of Texas where we can go 80.
Yeah. So you're traveling 80 miles in 1 hour if you're traveling at that speed consistently. Yes. All right. A, using what you know about distance, rate, and time, write an equation for this situation. Be sure to define your variable. Remember way back when we were talking about equations and inequalities, we had to say this little phrase, let, and then we had a variable. So I'm going to say let blank represent, and then it's whatever we don't know, right? What we don't know is the amount of time. Do we all see that?
Yes.
Okay, so we'll just say let something represent time. Because I'm going to be like a little more general instead of just saying hours.
So like
Okay, so t, I think that's a great variable. Let t represent time. You'll often see variables not in, I guess I should say it like this. You'll often see variables italicized. You see how my t like is kind of a fancy t? They're doing that so that you're not confused that it might be an addition symbol. That you know, nope, that's a variable, okay? All right, let t represent time. We've defined the variable. Now we've got to write the actual equation, okay? So 40 miles per hour. T is the time. So we're going to represent the time times 40 miles. 40 miles times the time. And I'm trying to get to 110. We're going to try to solve this. This says 40 times t. How do you undo this? Divide it by 40. And whatever I do on one side, got to do it on the other side. I'm going to give you like 30 seconds to start this. Go. By the way, the part of you solving it is technically B. A just asks for you to set up what the variable is and set up the equation. B says solve your equation you set up. How you doing so far?
good.
Good. Did 40 go into 1?
No.
40 go into 11?
Yeah. No.
No.
Wait.
40 go into 110?
Yes.
How many times? How many times? 2 times, which is 80, right? Okay. 0 minus 0 is 0. Can't take 8 from 1, so regroup. 11 minus 8? 3. Okay. So 2 and 30/40ths. That can be reduced. Divide by a 10 out over 10, right? A giant one of 10 over 10. So 2 and 30 divided by 10 is 3. And 4 divided by 10 is 4.
You can really just take the zeros off of them.
Totally. That's what dividing by 10 does, right? Is it takes away a place value. So this is time. And our time was in hours. So 2 3/4 of an hour. Okay, that is our answer. When we talk about hours and we say 3/4 of an hour, think of time. Like if our time was cut into 4 chunks, those are 15-minute chunks, right? This is where math gets kind of tricky because we go by a 60-minute hour, not a 100-minute hour, right? Most of what we do in math is based on 100 or 10, not time. Time is in these funky 60s, right? So think of a clock. I hope we're thinking because we're not going to lunch. We're thinking about math right now. Think of a clock. It's divided into 4 chunks, right? Each chunk 15 minutes at a time. This is 3 of those 4 chunks. So 15 and 15 is 30, plus another 15 is what? 45. So this is 2 hours and 45 minutes. Does that make sense?
Yeah.
Because 3/4 of an hour, 15, 15, 15. Okay? I want everyone to write that with me. 2 hours and 45 minutes. Because that's how we would actually say it. Mathematically, this is not wrong. 2 3/4 of an hour. 2 3/4 of an hour. You probably hear people say it this way. This is probably more common. Alrighty. Push in your chairs. Go wash hands, all of you. Come back and line up.